The topic of today is the basics of sound level measurements. Of course, this is a huge field with plenty of details and aspects that we might cover, so we had to restrict today's presentation to the most fundamental topics, to the most fundamental aspects of sound level measurements. Nevertheless, we have already planned to follow up some further webinars on sound level measurements, and these future webinars will cover more detailed, specific aspects of sound level measurements. You will, of course, be informed by email about these webinars. Let me introduce myself. My name is Markus Becker. I'm the Technical Director here at NTI Audio. And sitting next to me today is Berno Niksch, our Product Manager. He's assisting me during this webinar, and he will mainly take care of your questions. We have split the topic of today into 6 chapters, starting with the most fundamental information, followed by some explanations regarding the dB unit and measuring microphones and calibrations. Then we have also prepared a practical presentation, followed by some application hints. And we will conclude the webinar today with a Q&A session, so at latest at that time we will answer your questions and provide some auxiliary information. The overall duration should be in the range of approximately 30 minutes, depending also on the number of questions you have. First, let us ask, why are we measuring sound level and what are typical applications? This could be, for instance, the measurement of environmental or neighborhood sound, or another one would be monitoring a live event, or verifying or optimizing a sound installation, or last but not least, the qualification of machinery or industrial noise, or maybe there are even more applications you know or you could imagine. Nevertheless, the common aspect of all these applications is that we want to determine the noise emissions to humans. So we want, for instance, to quantify the noise pollution, or we want to identify annoying or hazardous sound levels, or, as I said, optimizing a specific environment or installation. So it always has to do with the impact of sound on us humans, on our hearing perception. What are the typical measurement parameters? Let's take a short look on the graph below. The blue curve shows us an example of what we call instantaneous sound pressure level. So this is the sound pressure level that is present at our measuring microphone every few milliseconds, for instance. So you can see it's changing pretty rapidly. It has high fluctuations. So it would be rather difficult to get an overall picture of an event by just watching this instantaneous sound pressure level. And for that reason, in most applications, we are using the LEQ. EQ is standing for the equivalent continuous level over the full recording, so over the measurement duration. And this level is a very good correlation to our human perception. At the end of an event, for instance, if we look here at the end of this event, this value that we can see here would give us a very good picture of what we, being present in this event, would have perceived of the loudness. The higher the level, that would represent what we would say this has been a loud event, for instance. So the LEQ is the most important, the most relevant measure to identify or to correlate to the human hearing perception. Then we have some additional weightings. Actually, we have the frequency weightings and time weightings. These are 2 different approaches, and we'll come back to that on the following slides, what they mean, where they come from, and when they are going to be applied. And another possible measuring parameter would be the minimum and maximum level that has occurred during the measurement. This is also in some standards, in some applications, a required measurement. So let's start with the frequency weighting. Again, the question, why do we need or why do we apply a frequency weighting at all? So the reason is quite simple. Our human hearing has a specific performance, saying that our perception, our hearing perception is quite good in the mid-range audio frequencies, but it's declining, the sensitivity is going down at lower and at higher frequencies. And this is shown, or this is reflected by these frequency weighting curves. If you look at the A weighting curve, that is a curve or a filter in technical terms that is representing our hearing performance at low sound levels, for instance, in the range of 40 dB. If we increase the sound level, let's say to 100 dB, then the curve changes its shape. So then we are talking about the C weighting curve that you can see here as well. So this would be representing our hearing perception at higher sound levels. And then we also have a kind of a technical weighting. Actually, the Z curve, actually this is no weighting at all. This is just a linear representation of the incoming sound. So the test instrument does not apply any weighting at all, any frequency weighting. And that is in some rare cases also required by the standard or applicable. If we look at the time weightings, things are a little bit more complex. So I'm going to try to explain that to you. If you look, for instance, at this old style meter, volt or sound level meter with a needle which is coming up as soon as the incoming sound level is increasing. The design of these meters was made in a way that they should rapidly follow a rising level in order to detect the peaks of that level, because this is necessary to avoid clipping, for instance. But then they should stay at this measured level for a short time so that the reader could have the chance to read what the measurement, the correct measurement value, the position of the needle. Now, if I translate that into the diagram below, which is, by the way, a simplified diagram, it's not a really scientifically exact representation, but I use it to show you the basic behavior of these time weightings. We have here a sound pressure level which is apparently pretty low, then coming up rapidly, staying there for a while, and then going down again. So what would that mean if we translate it into this behavior, into the ballistic of this analog meter? The attack time, saying the time it takes for the test instrument to reach the correct level so that the displayed measurement results corresponds to the actual sound pressure level. So there's a certain attack time or certain delay it takes the instrument to settle to this value. And this is what we call the fast weighting. This was actually the first implementation. But then people realized that in some applications we needed a slower behavior of the test instruments, a higher inertia, and for that reason the slow weighting was introduced, where the attack time or the delay is longer until the test instrument shows the actual value of the sound pressure level. But also the decay time is lower. This is the asymmetry, shows that here we have a longer time to read back what has happened here, what was the level up here before the instrument goes back to its initial position. However, if we talk about short impulses, both the F and the S weighting, the fast and the slow weighting, have its limitations because they may not reach actually the correct level of the sound pressure level. They're too slow. And for that reason, the impulse weighting was introduced with a very short attack time and even prolonged release time or decay, so that there is enough time. For instance, in this case, there's a short attack which reaches so that the measurement result is quickly reaching the actual sound pressure level, and then you still have some time to read this value. What are typical applications? The fast weighting is the most popular, the most frequently used weighting by far. The slow would be used, for instance, if we want to get an impression of speech signal, of my voice, for instance, because a human voice has modulations in it which would make the fast reading a little bit nervous. The slow weighting is a little bit more slower, so it's better representing the correct sound pressure level. Whereas the impulse weighting could be applied, for instance, in a shooting range where you have very short, very sharp, impulsive noises. But keep in mind, the fast weighting is by far the most frequently and the most frequently defined time weighting. With this slide, I want to explain a little bit the difference between the LEQ and the fast and slow time weighting. Keep in mind, the LEQ was the most relevant long-term measurement that would correspond to our hearing perception. Now let's look first of all here at the standard definition, which is pretty complex with time constants and decay, so I think I better explain it in a graph. Again, we take a look here at the recorded instantaneous sound pressure level, the blue curve, and the LEQ, this integrated curve, which is much better representing the long-term behavior of what has happened during the recording time. Keep that in mind. We put it a little bit aside, and now we introduce a new axis, the weighting. So what does it mean? Let's take a look at the LEQ measurement. The LEQ measurement takes all these individual samples from the blue curve, all the individual sound pressure levels that have been measured during this time, and calculates them into the LEQ result. And all these points go into this calculation absolutely equally. There's the weighting, the weight of each single measurement result of each sample is exactly the same as the other one, regardless how long ago they have been recorded. And here's a big difference to the fast weighting, for instance, because for the fast weighting, only the very last sample would be weighted by 100%, whereas the last but one sample already has a lower weighting. The next previous sample would even have a lower weight, so only the samples within the first second basically play a role with rapidly declining weight. So this fast result is a glimpse of the very last thing or the very last sound pressure that has happened during our recording. And the slow, by the way, is basically the same like the fast, but with a little bit slower decay, so there are more samples going into this slow result calculation. Once again, LEQ, all the samples through the whole measurement, even if it's 2 days, all samples go in with the same amount, with the same weight, whereas fast and slow, only the most recent samples are considered for the calculation. Then for the maximum and for the minimum, we have a rather simple graph to explain that. Here, for instance, the maximum would always follow the maximum level that has occurred to the corresponding point. So every time a higher level occurs, the maximum result display would rise to the corresponding value. And if there is no higher peak since the last one, it just stays there till the end of our measurement period. And the same, of course, applies for the minimum level, just in the opposite direction. Here, I'm only looking at the lowest sound levels that have occurred during our measurement. Talking about measurement types, so far we have been looking at wideband level measurements, which means that we considered all the sounds within the audio band from 20 Hz to 20 kHz, and we put them into one single value. For instance, here the LAF would give us one single result, or the LAQ has another result. Maybe for certain applications it's helpful if we get a clearer picture of this frequency distribution, and this is actually done by looking at the spectrum, which can be done in two different ways. The first one would be the octave spectrum, or third octave, sixth octave. These are just different resolutions. So here we get a better picture in which range, in which frequency range the sound pressure levels are mainly present. So we have a clearer picture of the behavior of the room, for instance, in which we are, or of the sound that has been generated. And if we need an even higher resolution, we would go for the FFT. This is a high resolution spectrum, which gives us even more information if this is required for your application. So we have been talking many times already about dB. What does dB mean? dB is the typical unit by which sound pressure level is measured or expressed. Actually, we should rather use the term dBSPL or dBA or dBc, whatever. But generally, we just talk about dB. dB is calculated by this formula. And what is very important, dB is a relative unit, not like volt, which is an absolute unit. dB is a relative unit, so we need a reference value. And this reference value in the world of sound level measurements has been defined by 20 micropascal. This is actually our hearing threshold, the hearing thresholds of us humans, typical hearing threshold of us humans. So this 20 micropascal go into this formula. So we measure the actual sound pressure level in Pascal divided by the 20 micropascal, take the logarithm and multiply it by 20. And that gives us the dB result. Another important aspect is that dB is a logarithmic unit, as you can see. And that has a big advantage because our ear is basically also working like a logarithmic device. So there's a pretty good correlation between dB and our hearing perception. And this also means that, for instance, if we increase a sound level by 20 dB, this means that the physical sound pressure level is actually 10 times higher. And it doesn't matter where I add these 20 dB. For instance, if I go from 80 to 100 dB, this is again the same. It means that the physical sound pressure level will raise by the factor of 10. Please keep in mind, dB is not directly an indication of the perceived loudness, only if we measure the correct parameters, for instance, the LEQ, as mentioned before, then we're coming close to what we humans would perceive as loudness. Few words about measurement microphones are very important. Behavior of a measuring microphone is that it has an omnidirectional characteristic. And that means that regardless in which angle the sound is coming to my microphone, whether it's 0 degree, which means from front, or any other angle, the sensitivity of the microphone should always be the same. And the second performance parameter is what we call the classes. So here we characterize the measurement microphones by their linearity or accuracy, about the residual noise floor. This is very important, for instance, when you want to execute a measurement in a very silent room. There you need a measurement microphone with a very low residual noise floor, because otherwise the noise that is generated by the microphone itself would compromise the measurement, would falsify the measurement. The temperature stability and the drift over time are, of course, also important parameters to characterize a microphone. Here on the left-hand side, by the way, you see a typical tolerance chart for a class 1 microphone. So the frequency response of that microphone must be very linear within a very tight allowance range, whereas for class 2 microphones, this tolerance limits are already wider. Generally, we recommend to use class 1 microphones because with them you are on the safe side. Regarding calibrations, we differentiate between two calibration types. The one would be the device calibration. For instance, every test instrument that is leaving our factory will be calibrated, which means it will be verified against our specifications. Does it comply to all our specifications? However, if you want, for instance, to execute a type-approved measurement, maybe you have heard already, the XL2 is now a type-approved instrument. In that case, to verify that, you have to send the device to a accredited calibration lab who would then execute this type-approved calibration and give you the corresponding confirmation. The second type of calibration is rather a verification of the microphone sensitivity. The sensitivity is kind of the factor by which the microphone translates the incoming sound into a voltage. And the voltage is actually the value that is then analyzed by the mesh test instrument. So this factor by which the microphone translate the incoming sound to this voltage is called the sensitivity. And the sensitivity is, for instance, talking about our NTI microphones, is saved in the microphone. So the device reads the sensitivity and now knows exactly which sound pressure level corresponds to which voltage, so it can display the correct measurement result. But just to be sure that this is working fine, we recommend to calibrate or to verify the sensitivity. And for this purpose, you need a calibrator. This is a technical device that can create a specific sound pressure level very precisely at a specific frequency. You plug that into the microphone, and then there is a simple routine on the test instrument that verifies whether this corresponding sound pressure level is coming in correctly to the instrument. So this is a measure to verify whether the stored sensitivity value is correct. Well, we're at the point of our practical presentation. I have here next to me an XL2 instrument, which is connected via USB link to my PC. On the PC, I have the projector software, and the XL2 is basically measuring the sound that is coming from my voice. So I'm going to switch over to that projector software so that you can see what the XL2 is actually measuring. The first thing you may notice is there are only two values visible, or two measurement results already active, the LAF and the LAS. And the reason for that is quite simple. These are kind of instantaneous measurements. So they don't care about what has happened 5 minutes ago. They are just measuring the sound pressure level of the past few milliseconds by applying the different time weightings as explained before. In order to see the other measurement results, I need to start the measurement. That's what I'm doing right now. You see it down here. This is the play symbol. And as soon as I have pressed that button, you see already the LAQ is coming up and settling pretty quickly to the average, almost average sound level that is present in this room due to my voice. You also see here the LAF max and the LAF min are now being displayed. So this was the most silent moment since I started my measurement, and it was the loudest one. And now you can see what happens when I clap in my hands. You see all of a sudden the maximum rises up and stays there until I would, for instance, clap another time even louder than before. Another thing you may notice now during my speech is that here, as I mentioned before, the LAF is jumping up and down pretty quickly, so it's rather difficult to determine the average sound level of my voice, whereas the slow weighting is more accurately and more stable displaying this level. So this is the advantage of the slow weighting, but this is a very specific case. As I said before, in most cases the F weighting is the one that is applied or required by the standards. And another thing I would like to show you, by just pressing one button on the instrument, I can switch over to the spectrum display, the third octave display in this case, and this gives me a very good feedback on the spectral distribution of my voice or of the sound that is present during my measurement. Good, let's stop that and get back to our presentation. We are now at the application hints. This is important before you actually start a measurement, before you go to a place where, for instance, a client asks you to execute a specific measurement, a specific verification. Please make yourself acquainted with the national standards that are applicable so that you select the corresponding measurement functions and weightings, the correct ones, the ones that are required by the standard. Second, we recommend, at least from time to time, to calibrate or verify the microphone sensitivity as I showed to you before. Then when we talk about the measurement itself, please make sure or take care about the position where you measure and also about your own position. And I would like to explain that with this picture. We have here a room with a person standing inside, and he is holding apparently a microphone or the test instrument. Now we have two sound sources, one coming from the left here with this green waves, and the other one from the right with the blue ones. What happens to the sound that is coming from the left? It reaches the microphone, so the test instrument would of course recognize that and give you the result, but these sound waves are also reflected by the body of this person. So here we have a superposition of the direct sound plus the reflected sound. And as you can imagine, this would always already have an impact. So the test result, which should be the one just from the sound, from the external sound, would be somehow falsified. The same happens with the sound from the right-hand side. Here we have a different effect, what we call the shadowing effect. Maybe you see here these curves are, there's a kind of a gap in between because the body of this person is shadowing this sound source versus the microphone. So in both cases, the person standing here holding the instrument has an impact on the test result, and that is basically what we do not want. Furthermore, take care about the height in which you are holding or positioning the test instrument. Whether it's a seating area like in a cinema, you would position it in a lower position like in a standing area. So in order to avoid these negative effects of yourself who are holding the instrument, we recommend, especially for precise measurements, for verifications, to use a tripod where the microphone is mounted on. Only this way you can really ensure relevant and correct results. And another aspect that should be considered, please log the measurement results. This is a short setting that you also have to do before you start measuring. Keep in mind the XL2 is able not only to save several measurement results in parallel, for instance the 5 ones that I showed you before, it can be even more, can be single value results plus spectra, and you can even in addition also log the wave file, so you can use the instrument as a kind of a sound recorder. And this has a big advantage when you go back to your office and you do some post-processing. You take a look at the results that you have recorded over a certain time period, and maybe you notice some impacts, some high impulses that have occurred. Then you can listen to what has happened and you can identify, for instance, has that been a sound that has been generated by the system you want to verify, or is it some external noise that possibly has to be cut out. So log the measurement results in order to allow the post-processing and of course a proper reporting for your client. Well, we are at the end of our presentation. We'll just take a look at the questions that have come up. But before, please, if you have any questions in the future, do not hesitate, contact us or contact any of our subsidiaries or independent sales partners worldwide. They will be happy to support you and answer your questions. And once again, the recording of this webinar will be published with a short delay of a few days. So we will inform you about that if you want to listen again to it or share it among your colleagues. So let me take a look at the questions that have come in so far. Okay, I see one question regarding calibration. The question is, how frequently should the XL2 be calibrated? We recommend an annual calibration of the unit, saying that you should send the unit if you really want to do reliable measurements and want to be on the safe side versus your client, send in your instrument once per year to us or to our subsidiaries to execute such an calibration. Then I have another question regarding the frequency weightings. The person is asking whether the B weighting curve is also implemented in the instrument. Maybe you remember the picture with the frequency weightings. We had the A weighting curve and the C weighting. Actually, there was also, or there is, a definition of a B curve, which is something in between. However, over the past years, it turned out that this B weighting is not really providing some relevant information, and for that reason, it was kicked out from all applicable standards. You won't find it anymore in any standard. Only the A and the C weighting have survived. So for that reason, we did not implement the B weighting just because it's no more used. It may have been used some 20 or 30 years ago, but this time is gone. Nowadays, you just need the A and the C weighting, and that is what is, of course, implemented in the XL2 together with some more weightings, but I'm going to present them to you in another webinar. Then there is another question regarding executing measurements by holding the instrument in the hand. Basically, yes, of course, you can do it. And when you, for instance, want to execute a first assessment of a certain location of a room, it's absolutely practical holding the instrument in your hand. It's very easy to read the results and everything. It's not very time consuming to put because you can do it directly. But as I said, it's better or mainly used for assessments. I would definitely, when you have to do a very reliable, very accurate measurement, please put the microphone on the tripod rather than holding the instrument in your hand. You can, of course, stretch out your hand, but still your body will have some impact on the measurement result. Just keep that in mind. It depends on the application. Well, and then I see that's another question, very good one, regarding the orientation of the microphone. You remember the picture I showed to you? The microphone was, look, I can just go back here. You see it here. This picture shows the microphone as it is pointing horizontally. Actually, if you have an omnidirectional microphone, the orientation is not really important. Nevertheless, I would recommend to again adapt that to your application. For instance, if you're standing in a room and you want to measure the sound coming from the stage, maybe you don't have to, but you should better point it towards the stage. If you have an environmental measurement outside, traffic noise, whatever, you could point it vertically. It's not really decisive. It's also a little bit of a cultural question. We realize that here in Europe, people tend to hold the microphone in most cases horizontally, whereas in the US, it seems that the vertical position is more popular. Both of them are applicable, both of them are okay, supposed that you have an omnidirectional microphone. Yeah, now I see another question regarding these Class 2 microphones. What's the purpose or the application of a Class 2 microphone? First of all, of course, Class 2 microphones are less expensive because the capsule is less demanding to manufacture, and so you have an advantage regarding price. And Class 2 microphones are good microphones. I don't want to blame them for anything. So you can use them also in many practical applications. But again, if you have a application where you have some kind of responsibility versus a national standard versus a client who might need to be to verify or to prove the sound level over a certain time due to the law, then I would definitely recommend that you rather use a Class 1 microphone. For a initial optimization of a installation, you can of course also go for the Class 2 microphone. Good. I think we are at the end of our webinar. Thank you again very much for your attendance, for your interest. And we will inform you, of course, about the upcoming webinars with the more in-depth information about sound level measurements. Hope you enjoyed it. Hope it met your expectations. And I'm wishing you a very good day and see you again soon. Thank you and bye-bye.